All right, at this point, the stream should be on. We're not yet ready to start for a little bit, but we are running some tests to make sure this whole thing works. I just saw on the little diagram that YouTube Live gives me that there should be about 6 computers connected at the moment. So hopefully somebody can hear that. I'm just gonna chill out here for a little bit and see if anything comes in. And there's me. I see myself on my phone, so we're definitely running. Cool. There's no chat, as you can see, so there's no really reason for this to be live, but we'll see what happens. Cool. All right, we're still waiting, but everything appears to be connected, and I've confirmed that things appear to be working at the moment. Moving the slides around is working, so this is great. Cool. Maybe I'm gonna put this here. I've lost the sound. Now for the necessary fidgeting of all the crap on the desk. Don't want to zip anything there. Actually, can I? I'll go back there. There we go. Yeah, don't have that. Should be fine. Cool. We've had to change some things behind the scene really, really quick. So we're making sure the whole committee has access. Great. And great. Great. I'm seeing from Jennifer and the rest of my family back home that you can hear me. That's great. Hopefully it sounds pretty good. To you guys back home, this is the awkward part where we sit and wait for things to get ready now that the stream has been properly tested. Great. All right, I'm gonna take a step out and be back in a second. Okay, hopefully people can hear/see me again. We just had a total internet disconnect here at Clemson. I've been given special permission to use a office, a totally empty office, to run the live stream from the hopefully good internet signal here at the university. So hopefully it doesn't cut out again. That could be pretty detrimental. Yeah. Okay. Can you see me now? Great. Here we are. Touch through the slides. Great. I'm getting confirmation that people can see the stream on the other end. So hopefully this doesn't totally explode again. And the internet not on campus has not glitched. Okay. Great. You can see the stream. Awesome. Okay. Cool. We're only about 10 minutes out now, so hopefully nothing breaks. You know, that break we just had actually tells me that if we do have a terrible disconnect in the middle of this presentation, that hopefully things should go fine. Because it appears as if once the internet comes back up, I can just rejoin the call and the stream is configured to keep churning along with a couple of, button presses here and there. I saw a second ago that there were 9 computers connected to the stream, so thank you, all 9 of you out there. Hey, Amy, have fun.
Hey, how are you?
I'm doing good. The internet just disconnected for the whole building, so we're gonna hope it doesn't happen again.
Okay, well, my internet went down this morning right in the middle of my class. I was running Zoom, it was going great, and then I dropped out. It was to my house.
Yeah.
And I wasn't planning for that. So I had my cell phone.
Mm-hmm.
Yeah.
Yeah. I mean, that's pretty much where we're at here. The Wi-Fi disconnected and the wired connection disconnected. So great.
Yeah, I couldn't believe Google. So I did go check the AWS infrastructure and it's all green.
Oh, that's great.
To be happy.
By the way, you're on the live stream at the moment, which I just configured so that like family members could watch. Yeah, great.
I may make my video go away in just a minute.
That's fine.
It's nice to have like a human contact,
Yeah, yeah.
How are you doing?
I'm doing fine. It's been a little crazy, but my house seems to be a pretty decent place to get quarantined in. I've got like a neighborhood and some stray cats have shown up, which is pretty fun. Can't disinfect the cats, but it's what I got.
Seems okay. Yeah, I think I probably will turn my video off when you start. If nothing else, than to preserve bandwidth.
Yeah, that's fine. Yeah.
Do you live right in Clemson?
No, I'm actually in Newry, which is north of Seneca.
It's like I know exactly where that is. I live
okay.
When it pops up on my location finder, it thinks I'm in Newry.
Ah, okay. Yeah, Newry is like 12 buildings and then one down mill. So,
yeah.
Yep.
We had another graduate student that was renting an apartment in Newry for a little while until she moved to Greenville.
That makes sense. I just don't want to do the drive.
No.
Yeah.
So do you live in a house or is there like an apartment building down there?
It's like a duplex, so it's half of a house, but it's pretty cheap because it's in the middle of nowhere.
Yeah.
It's nice. How are you surviving other than the internet disconnecting?
Good. I mean, the main problem is that every day feels like Saturday.
Oh my
because I always work from home a little bit on Saturday anyway. So I get up and I do some work and I'm okay. I've worked for a while. Now I should go get to do something fun that I want to do. I'm like, no, you're at work. You have to keep working.
Yeah. Pulling myself out of bed is the hardest part of the day.
Yeah. No, my house is actually pretty pleasant. It's just weird being here all the time.
Yeah. Well, I'm just hoping that we don't have any terrible technical problems, and then I'll be good.
That too. I mean, in the worst case, you've sent us your slides.
That's fair.
I could host a 4 or 5 way cell phone call.
Exactly.
Actually, really seriously as a backup, do you have everyone's phone number?
No, I don't think so.
Let me share my contact information with you. What is your phone number?
Yeah, here, let me send you an email. It's 484-354-8692. Yeah, and then if you could just send some stuff over.
Say it again.
484-354-8692.
484-354-8692.
Yeah, the first 3 digits were 484, just to make sure.
That worked.
Cool. Cool, I got him. Great. Worst case scenario, I'll call everybody.
Yeah. So Justin, what are you going to do after you graduate?
Well, the summer is a big question mark. I was planning to travel, but we'll see if that's possible. And then I'll be working at Google Brain in August, starting in August.
That is exciting.
It is
Some companies are moving, like these tech companies, are actually moving up their start dates.
Oh, I'm not surprised. I think there's the idea that it's just going to get worse.
Yeah, so if you get into a situation where you wish you were working, you might just contact them and see if they'd let you start sooner.
That's fair, yeah. Well, I'm hoping to enjoy a little bit of a break, but we'll see.
Yeah.
Yeah.
Be nice.
I'm not really looking forward to quarantine.
No, not so much.
Hello, Justin. Can you hear me?
Yeah, I can. There we go.
Okay, very good.
We'll
Good.
see
Okay.
yet, but
Hey, Elia.
Hello.
great. Said she wouldn't be joining, so we're just waiting on Dr. Dean.
Okay, but you're
Hey, Alex.
recording, right?
Hello, how are you?
Yeah, I'm recording. The stream is happening right now, so this is all being broadcast, by the way. And it should work, assuming we don't have a catastrophic failure.
Does YouTube work?
Yeah, it should be. I have family members who are telling me that they can hear this conversation right now. Yeah.
Very good.
Okay, so just so you know, I might be turning off video while
Sounds
you're
good.
talking and maybe mute
Mhm.
because there might be kids in the background.
Great.
Yeah, I actually did that
I'll
too.
also mute.
Mhm.
Maybe not a video, but I'll mute for sure.
Cool.
Yeah, but I'm listening all the time, and if anything comes up, I will unmute.
Great.
Sun's coming
Waiting
out.
for
I see blue skies.
Great. I haven't heard back from Brian since we changed the call details, so hopefully he gets that.
Do you have his contact information?
I don't think so. Yeah, Amy and I were just talking that if worst comes to worst, I'm getting everybody's cell phone numbers so we can take this to a group phone call if need be.
Yep.
Yeah, I don't know about you guys. I could host a 5-way phone call on my cell phone, assuming I have cell coverage. And he's already given us his graph or his slides.
Actually, have I given you the slides? Let me send those out again.
Okay, so I shared Brian Dean's contact information with you.
Great.
Okay, that's neat. I can confirm that the YouTube live stream is working, but it's lagging by a few seconds. So
It's supposed to lag for a few seconds. That's what makes it not freeze up and crash.
okay,
So
it's fun because I could just re-listen. I had a déjà vu.
Yeah, I was not intending for any of you guys to be watching the live stream while we do this, so hopefully the lag doesn't matter. Alex, how have things been for you during shutdown?
It's good, can't complain too much. Schools are closed, so we have both kids at home, our 4.5-year-old and 1.5-year-old.
Yeah.
And because we're both working full time, that's a bit of a struggle. But we can't complain. I can do all my classes online. We have a nice backyard to entertain the kids, so things are going well given the circumstances. And nobody is sick. That's the most important thing.
Oh, good.
Yeah, that's
Online
great.
classes are really good. The online classes are going really good.
Cool.
Yeah, I'm surprised too. The technology is actually working really well.
Except when my home internet dropped out this morning. That was a problem.
Yeah, that becomes a problem. Yeah.
Called in via cell. Justin, did you have any trouble getting into the building?
I didn't. Interestingly, they had like shut down some of the doors on this floor, but I just found another staircase and it worked fine.
How did they do that?
Well, like I think they disabled like the electromagnets to keep them open, and then they automatically lock. I'm not sure.
I did not think about that problem. So which way did you come up?
I took the staircase that's closer to like the IT guy's office, like around where Sausage sits.
I wonder if the elevator works.
I haven't checked that. I think it does because there's some cleaning staff here that I think are using the elevator.
I didn't think about that problem. I'm glad you got in.
Justin.
Yep.
Can you email me your YouTube live streaming address?
Yes.
Some people want to watch it and they cannot connect to Zoom for some reason.
Okay.
So yeah, if you could just email me the link, and then I will forward them.
Pull that up.
So you'll have other guests, not just your family, for sure.
Great. Yeah, I've been trying to publicize it. So we'll see.
Amy, do you have Brian's phone number?
I do.
Yeah, I texted it to Justin just now. Do you want me to share with you too?
Okay. Yeah.
I assumed, Justin, that you had Ilya's phone number, so I didn't.
I might, I think. I sent it to you over Slack.
Okay. All right. Yes. I see it. Yeah.
Okay. And let me text.
So the rule for says, since she is not here live, is that she's still a committee member, but she has to abstain on any vote.
Okay.
So she can vote, but her vote has to be abstain. And actually, since 3 out of 5 of your committee members are here, I guess we could declare it's a quorum. And so if something happens with Brian, we could still go, oh, there's Brian.
We have Brian. Yes.
Oh, great. Okay, perfect timing.
Hey, we have Brian.
Sorry, my computer decided to hate me for the last 5 minutes.
Okay. This feels familiar.
All right, so I'm going to turn off my video and mute, and but I'm still here.
Great.
Yep.
Okay.
Same here.
So I'll mute too. Okay. All right. So I think we can start.
All right.
Right. So Justin did a lot of excellent work, and hope we'll hear at least part of it during next hour. Okay, good. So I'm muting my microphone, and feel free to ask questions. And those of you who are on YouTube, please email me your questions if you want to ask Justin, and I will filter them out.
Yeah, and if anybody who already has a contact information for me that will make my phone give me a notification, I will happily answer questions from that.
Okay, good.
Great. All right, so thank you everybody for being super flexible with all of the technology issues we've had. Hopefully we don't have too many more, especially my committee members who have had to change some technical details behind the scenes. I'm very happy to talk to you guys about the work I've been doing over the last 4 years in this dissertation defense called Exploiting the Latent Features of Text and Graphs. So before we get too deep into the details, I'd like to take a second to talk about some of the accomplishments I've had over the last 4 years. This is primarily in 7 first author publications, 3 we've published, 4 are in the works, and these are what we're going to be focusing mostly on for the next about hour. I want to also mention some work I've been able to help out on as a co-author, including some work in the biomedical domain and structural engineering, as well as some upcoming work in some psychology research using machine learning in interesting ways. But beyond academic achievements, I've also had the chance to work on a couple of internships in industry. I've worked at Los Alamos, Google, and Pittsburgh, and I'm very happy to have accepted an offer to work with Google Brain in Pittsburgh starting in August, everything considered. So without further ado, let's get back to exploiting the latent features of text and graphs and unpack what that means. So our ultimate goal is to understand the underlying distributions of our data sources so that we can make some non-trivial inferences about what we think this data set is going to do in the future. Tons of people do this in machine learning, but we're going to focus on automatic hypothesis generation for a majority of this talk. So the goal here is to predict new research ideas using historical information. This information comes in a number of unstructured formats, specifically the papers that people are publishing where they talk about their new ideas, and the connections that they've already found between different entities of interest. This type of work can apply to many types of sciences, but we're going to be focusing in the biomedical domain later in the talk. And so now we're going to get a chance to talk about some of these works. Each looks at the underlying trends of data sets in kind of interesting ways. We're going to start with some work in graph embedding. And after going through some things we've learned in graph embedding, we're going to talk more about hypothesis generation and all the ways we've looked at that. I'm going to focus primarily on these final 2 papers. These works we have currently in submission to KDD, and I wrote them in, I think, February. And the committee hasn't had a chance to see them yet. So I'm going to give more details on that when we get to it. But let's get back to the basics. I want to tell you about a structural building block that we're going to see repeat many times in this dissertation, and that's embeddings. This is the mechanism to which we're going to learn these underlying trends of our data set. And as opposed to some sort of statistical model where you have an idea of what trends you'd like to capture, and so you learn those trends from your data, embeddings allow us to kind of broaden that understanding to create a much larger set of latent features. And although these features might not always be very interpretable, we're going to see they have a lot of applications in describing these data sets for machine learning applications. So the typical embedding model, which many of us have already heard of, is the skipgram model for text understanding. I'm going to bring it up mostly because it follows an interesting pattern we're going to see repeat. That is, first, we observe some similarity on our data set. The similarity that Word2Vec observes is that similar words share similar contexts. Once we've decided what similarity we're trying to look at, we're going to model that similarity using some numerical representations. In Word2Vec, a word's representation, or its embedding, is used to predict the other words that came along with it in a sentence. And in that mechanism, we are able to understand what company each word keeps. I ran a model just like that on biomedical text. And the model knows nothing about medicine or biomedical entities, but by looking just at the co-occurrence of these word relationships, we're able to pick out certain types of contexts that are talked about distinctly. For instance, here you see a 2-dimensional visualization of this embedding where each dot represents a particular word and the color represents a type of word. Well, we see that nucleic acids are all talked about in a similar context, and that's different than the context we see bacteria in. This should hopefully give you some understanding of the way we can capture some really interesting emergent behavior from our data sets using a rather simple set of observations. So now let's talk about how we can modify some of that intuition for graphs so we can understand some of our contributions going forward. Graph embeddings are really important, and we're going to use them a lot of times in this talk. A graph embedding is just asserting that there is something similar about different types of elements in our graph, and we want to place them in a vector space to capture that. Now, there's different types of similarities you might choose to observe, The deep walk model, I think, is the easiest to understand, so it's the one I'm depicting here. The deep walk model takes a random walk of nodes in your graph and treats that as a pseudo-sentence so that we can apply the skip-gram model. In this manner, similar nodes are those that share similar companies in random walks. And therefore, we end up capturing a combination of structural and homophilic features of our graph. Details of that are left aside, but the point here is that we can start to capture some really interesting hard to interpret results that can be very powerful for deep learning models. However, existing graph embedding methods have some limitations that we chose to explore for the particular case of bipartite graph embedding. Over the next couple of slides, I'm going to tell you about a way that we modified some graph embedding techniques in order to better fit bipartite graphs. A bipartite graph is one that has two types of nodes. I'm calling them A and B, and all the edges of a bipartite graph connect a node of type A to a node of type B. Now, existing graph embedding techniques can typically pick up on the existence of these two types, but they tend to be placed in distinct locations in the embedding space. Within a type, however, the type-specific latent features can sometimes be eroded, and those are the ones we'd like to capture in the methods we propose here. So ultimately, we'd like to learn this embedding function epsilon that takes a node in our graph and projects it into n-dimensional space. We propose two methods. The first is first-order bipartite embeddings. It looks just at local similarities within our larger network. It's actually rather simple, but has some emergent properties. So the thing we'd like to observe is that two nodes are similar if they share a similar neighbor or if they have an edge in common. We can model that similarity using embeddings by just taking the dot product of embeddings, represented here by the epsilons in the middle of this equation, and we can restrict that to the domain of the 0-1 interval in order to match the observations we've also captured. Now, you note here that we make a very simple comparison between two embeddings for the A and B type comparisons. But for the S of V, in which we make a cross-type comparison, we instead decompose that into sets of same-type comparisons. Here we're looking at the expected value of A and its neighborhood versus the expected value of B and its neighborhood, which will allow you to capture better type-specific features because you're no longer making strict assertions across the types of the embedding space. More details left in the dissertation. But with this formulation, we can minimize a simple divergence objective that allows us to plug into existing machine learning architectures like TensorFlow. And we can get some interesting results, which I'm going to talk about in a second. Now, the method I just told you about is very simple to calculate and only looks at local information. But oftentimes you want to capture higher order information. And the problem with that is in real world graphs, nodes will have many, many higher order connections, and they're not all equal. Some are going to be a lot more valuable to our embedding space than others. In order to approximate the importance of each of these connections, we turn to a heuristic called algebraic distance. Algebraic distance is a method that allows us to take the nodes of our bipartite graph and place them on the number line such that two nodes, if they are similar, should get similar coordinates. We run multiple trials of algebraic distance, iterating each until stability for speed reasons, and we can compare the location of two nodes by their mean squared difference across all of our trials. And with some simple normalizations, we can convert that into a similarity measure that's between 0 and 1, where 1 indicates a very highly similar pair of nodes. We can use that to influence our observed similarities. Now, two nodes are as similar as their most similar shared neighbor, if they're of the same type. If they're of different types, we can again decompose the cross-typed relationship into sets of same-typed comparisons. However, here we're not just looking at immediate neighbors, we're looking at neighbors of neighbors, which we're able to do because now we have this heuristic signal to help us. We can fit that using a very similar strategy. We train embeddings such that the dot product of embeddings conveys the similarity measure we've observed. And again, we decompose cross-type similarities into sets of same-type similarities. This can be optimized using a simple mean squared error objective, again, allowing us to plug into TensorFlow. So I've just told you about two different ways you might want to capture bipartite graphs. One which uses first-order relationships and one that uses higher-order relationships. we can actually combine the intuitions gained by both embeddings through this combination embedding we propose. This model takes a set of pre-trained embeddings as input, and through a combination of a semi-supervised approach, wherein we repredict edges from the graph, as well as encode the full set of inputs, we're able to, in effect, boost the disjoint signals of our embeddings and combine the redundant signals of our embeddings to get a oftentimes higher power joint embedding. The details of this are going to have to stay in the dissertation, but this combination approach is going to reoccur a couple of times. Well, we've done a lot of work. What do we get for it? The first way we choose to evaluate our method is through link prediction. And there's a couple of ways you can look at that problem. This is the problem of deleting some edges from your graph and trying to predict them back out with your embeddings. So we run a bunch of trials. In the horizontal axis, we see the problem difficulty, which corresponds to the number of edges left over, where a higher number is an easier problem. And the vertical axis is the quality that we get from our embeddings. All of the bold lines represent methods I've proposed, and the dashed lines represent the state of the art. The unified method you see on the far left, as I drop some stuff, is a method that uses both type of embeddings in order to predict the existence of a link. So our method performs about the same when you're not using type-specific features. The other two personalized methods are different ways to look at type-specific latent features in order to make the predictions. And here we see that when you're restricted to type-specific features, our methods outperform the state of the art on this example. There's a range of other examples left in the dissertation, but I would like to talk instead about another type of analysis we can perform, and that's recommendation. It's very similar, but in recommendation, we'd like to guess the priority that a user might rate some new connection. If you're on Netflix, we're trying to guess the star rating you might give a new video. Well, it turns out using type-specific latent features, we can again outperform the state of the art in a couple of different baselines. More details in the dissertation, of course. So that's a flyby of a new bipartite embedding technique that we've produced, and we've shown that it can apply to a number of machine learning problems. Now we take this method and we extend it so that we can apply the intuition we've gained from embeddings into an algorithmic problem, in this case of hypergraph partitioning. Hypergraph partitioning shows up in a number of applications, such as distributing data in large scientific computing applications, or placing a circuit on a chip. And so it's important that we get high quality solutions. But first, what's a hypergraph? Well, a hypergraph is just a traditional graph structure, except hyperedges may contain any number of nodes. It turns out hypergraphs have a one-to-one relationship with bipartite graphs. If you take each hyperedge and replace it with a node in your new type, you can see that the edges of our bipartite graph represent the participation of nodes in our original hypergraph structure. This relationship is important because it allows us to use our existing bipartite embedding techniques in this context. And so now we're trying to solve the problem of hypergraph partitioning. Algorithmically, this is the problem of taking the nodes of your hypergraph and splitting them into equally sized disjoint subsets such that we minimize some objective on the number of cut hyperedges. A cut hyperedge is just one that spans multiple partitions, and we either want to minimize the total number, which is the cut, or the number of parts spanned by each hyperedge, which is the connectivity. But regardless, this problem is NP hard to both solve or approximate. Therefore, we need to turn to some heuristic solution strategies to gain an approach to this problem. The gold standard solution is called multi-level hypergraph partitioning. It is multi-level because we're going to take our input problem, which is too large to solve directly, and we're going to iteratively coarsen it. In this manner, we're going to combine different nodes together such that our initial solution, or our most coarse subproblem, can be solved directly using an existing algorithm, but it maintains key structural features of our input. When we get this initial solution, we can then uncoarsen and refine that initial solution back to the larger initial problem instance and get a pretty good solution to this problem relatively fast. This little diagram you see is called the V cycle on account of its coarsening and uncoarsening V cycle. Okay, if you take a look at this, hopefully it seems apparent that the coarsening half is very important. The quality of our initial solution is only as good as the coarsest representation is similar to the initial representation. By that I mean we need to make sure that we capture the key structural features as we merge nodes together. And it turns out that the existing strategy to do that, while it's really good at capturing local information, can sometimes get rid of some global structural features. Let's talk about how you normally solve this problem of coarsening. Well, you need to, at each level of coarsening, pick a node. This is typically done randomly. And you compare that node to all of its neighbors based on some measure. A standard measure currently is called heavy edge coarsening, wherein each hyperedge is given a weight corresponding to the number of parallel hyperedges at this level of coarsening, details in the thesis. And whichever neighbor maximizes more or less the number of shared edges is the one we're going to coarsen together. Now you note that this only considers local information, and it turns out it has some undesirable effects in some edge cases. Here's a cartoon example that kind of tells you what I'm talking about. Our initial structure is a hypergraph of 5 nodes. 3 of them are merged together in an edge, and 2 of them are merged together in a second edge, and there's a couple cross-cutting connections. Now with heavy edge coarsening, there's 3 different contractions that are equally scored. However, only one of those contractions maintains the global structure of a cluster of weight 3 connected to a cluster of weight 2. We're going to use signals provided by a graph embedding to help us prioritize this sort of contraction that best preserves global structure. How do we do that? Well, we need to first change the random visit order because we instead want to prioritize those nodes that have very key similar neighbors. We do that by ordering our nodes in this visit order by the dot product of the embeddings with its neighbors. So here, the node we visit first is the one that has the most similar neighbor with respect to the embedding. Then when we perform the merge, we're going to combine heavy edge coarsening with an embedding-based measure. In this manner, a node that is contracted is one that has both local features in common and global structural features in common. With this, we get a lot of the way there, but we need to make one other modification. When we contract 2 nodes together, we get a new coarse representation within our hypergraph. We need to assign that node an embedding. It turns out that running our full graph embedding technique is both very costly and leads to decreased performance due to some convergence issues. Instead, we assign an embedding to this new coarse node that is equal to the average of the embeddings contained within. We're going to see that this has some strengths and weaknesses, which we're going to see in a couple of slides. But let's talk about some of the changes we've made, because they also come with some pros and cons. We'll see the pros in a second, but the cons are that we've increased the runtime in a couple of ways. First, you do have to perform a graph embedding before you start the partitioning problem. This way, you give your embeddings to each of your nodes as an auxiliary input to our partitioner, and we can run from there. However, you do need to pick some embedding. Now, right now, graph embeddings are about linear broad strokes, and they are typically very parallelizable. Also, because graph embeddings are a very evolving field right now, we're not going to focus too heavily on the particular runtime of any embedding. And we're going to note that it doesn't change the asymptotic runtime of this process, given the fact that they're about linear and very parallelizable. The ordering of our nodes, however, does change the algorithm from our perspective, because at each level of coarsening, you have to sort your nodes. It ends up working out that the ordering process does not change your asymptotic runtime, because you still have to make all nodes comparisons to score your neighborhoods, but you do end up adding a pretty sizable constant in the case that you really care about fast hypergraph partitioning. However, if you're willing to pay the cost in runtime, there are some significant performance benefits. We capture those by implementing our embedding-based coarsening in a number of partitioners. We compare 4, Kahipar and Zoltan, which are open source, and therefore we can modify them, as well as Pato and HMetis, which are closed source but provide an interesting baseline. Kahipar is also very interesting. It's the state of the art in hypergraph partitioning in terms of quality, and it has this optional flow-based refinement. So it's the other half of the V cycle, but it's a very smart way to do refinement that has led to some interesting performance results. So we want to make sure embedding-based coarsening doesn't affect that, and we want to see how embedding-based coarsening is affected by that. Okay, with that out of the way, we can look at some benchmarks. The benchmarks we run are very large and varied. We have about 100 hypergraphs. We look at different numbers of partitions. We consider different embeddings, including the ones I've just talked about. We look at both ways you could measure the partition, and we run 20 trials with different random seeds for each combination. We're going to be looking at different summary statistics for this. We're going to focus mostly on the macro mean, which is just the average performance across the whole benchmark. More details, of course, are left to the dissertation. Now, finally, we can get to the performance numbers. This table shows you, for each measurement, the improvement in quality gained by using embedding-based coarsening as compared to the same partitioner without embedding-based coarsening. We see for low numbers of partitions that Kahipar can get between an 8 to 16% improvement, and Zoltan can get between a 15 to 50% improvement, again, for low numbers of partitions. These results are really significant, especially because current embedding or current partitioning-based solutions, when they publish new performance-based numbers, strive for about a 1 to 5% increase. That's big in this problem. So we're really happy to see that embedding-based signals can provide some really interesting structural information that we can take advantage of. However, we see a decrease in performance as the number of partitions increases. This is because I mentioned that we are averaging our embeddings together as the graph becomes more coarse. This has the effect of smoothing our embedding space, and therefore removes a lot of the interesting and useful variance that you might need to find 128 parts within your hypergraph. We note that it doesn't decrease performance significantly, and it has some benefits on multiple partitioners, but we leave the high number of partition case for future work. But we can continue looking at our benchmark with a bit more of a thorough analysis. Here we see our average performance improvement, where a higher value is better. And we see the baseline, which is the horizontal dashed line representing the performance of Kahipar flow. And this is the current state of the art. Now we see our ticked bars, which are the methods proposed here. They still improve overall performance compared to the entire baseline, not just to its reciprocal method. And we see again that that performance decreases as the overall number of partitions increases. So this demonstrates that embedding-based coarsening can really drastically improve your solution to the problem, especially on some particular graphs that are described more in the dissertation. And it opens the research to potential focus on these high numbers of partitions. Anyways, with this out of the way, I'd like to take a second to transition from graph embeddings to this problem of automatic hypothesis generation. This is that problem I mentioned earlier in this talk, wherein we're going to be looking at the underlying features of biomedical research in order to come up with new fruitful research ideas. And when we get later in this talk, we're going to see graph embeddings make a reappearance in order to help us understand connections within medicine. So let's
Justin, just a second.
Great.
Because I switched the topics, does anybody have any questions about graph embedding part? Do you have any questions?
No questions yet.
Great.
Okay, good. So we can move forward.
Cool. Thank you. Okay, so automatic hypothesis generation. Our goal is to accelerate research by using the existing biomedical information to find new directions. One application that we focus on a little bit is the problem of drug discovery. Drug discovery starts by coming up with an idea of some disease you'd like to treat, and you begin by finding thousands or tens of thousands of different substances you might like to consider. And you very quickly have to winnow those thousands of substances down to about a dozen candidates that you're going to consider very thoroughly. And ultimately, this leads to about 1 or 2 human trials that, of course, could fail at any point. If this process completes in success, you go to market and make some money. But if this process fails, you could end up losing billions on lost research. So our goal is to try to give more information cheaper and quicker to decision makers earlier in this process. How do we do that? Well, we take advantage of the wealth of available information provided online. PubMed is a repository of medical abstracts. Its underlying database is called Medline, which I'm going to use to refer to this data set from now on. And it currently contains about 30 million papers. It's getting about 1 million papers every year, and that works out to a new paper every 35 seconds. As a result, it becomes very hard to keep up with the entire scope of the problem you might be dealing with, And as a result, there can be missed connections. One example of a missed connection was found in the mid to late 80s, and it was a connection between fish oil and Raynaud's syndrome. It took a machine learning approach to look at the correlation of keywords across titles of papers to identify that blood viscosity had a joint relationship to both fish oil and Raynaud's syndrome. This was findable in the existing medical literature, but until that information can all be put into a decision maker's head, we can't take advantage of it. Well, this finding eventually became accepted as a treatment for Raynaud's syndrome, fish oil that is, and it demonstrated the usefulness for a type of hypothesis generation. Now, of course, machine learning has advanced pretty significantly since this finding, and so we have taken some new approaches to explore the problem space, starting with our paper Moliere, which we presented at KDD in 2017, and is a very large data processing pipeline to help us understand biomedical information so that we can construct a very large network describing all of the relationships between entities. And we can do some network analytic techniques to extract key information from biomedical literature to help us make decisions. Let's dive into that a little deeper. We have a set of data. It begins as raw titles and abstracts, which is just the text available on this Medline data set. We can extract from it key phrases and also predicates, which are subject, verb, object statements. These can be combined and augmented with coded terms. So they're like numeric codes associated with different concepts in medicine. They're provided by this thing, the Unified Medical Language System. And it also tells us interesting synonyms, such as in this case, that neoplasms are the same as tumors. We can use all of this information to construct a large semantic network. On the left, you see the schema of this network. So the nodes and edges represent the different types of connections we represent. On the right, you see the way in which we make each of those connections, combining some embedding-based semantic understanding of our abstracts and keywords with simply occurrence-based information provided by other data sets. Details of that are, of course, left in the dissertation, but once we have this large network, the key thing that we choose to understand and model are shortest paths. So the way the Moliere system works is a user comes with two entities in mind. So for instance, a gene and a disease. And we find a short path within our network that briefly describes a potential connection between the two elements of interest. We extend that path to find a couple thousand abstracts per node for the entirety of this connection. And we collect maybe 10,000 abstracts related to the query of interest. The intuition here is that if a human being sat down and read all 10,000 papers, they would know for sure what this AC connection would be. We, of course, don't want them to spend that time reading papers. We instead do some of that analysis for them through a process called topic modeling. Topic modeling will cluster the keywords within our papers into the primary areas of conversation. And we can analyze the keywords within those topics in order to anticipate what potential connections might exist. We ran one example that I think highlights that, and it's between venlafaxine, which is a generic drug treating depression and anxiety, with two genes, HTR1 and 2A. So we know that the drug treats different genes, and we would like to predict which relationship exists. Now, we tried to predict this using information published before 2010. And in 2013, scientists discovered a connection with 1 and a lack of a connection with 2. Well, we uncovered that using historical data, and we found that by simply looking at the correlation of depression-related keywords across the topic model, that you see a correlation with 1 and a lack of a correlation with 2. So in that manner, we used some intuition and expert analysis to help us validate the Moliere system. And it works well for some very particular fine-grained queries, but we'd like to perform a much larger validation to get a broader sense of an understanding of system performance, and also hopefully allow us to run many, many Moliere queries in order to accelerate research in a real-world setting. For that, we did a lot of work in this paper on validation, which we presented at Big Data in 2018. So validation is really challenging for hypothesis generation, because the system is ultimately trying to find new research ideas that are unknown to even us building the system. So is the system acting oddly because we don't understand something, or the system is truly incorrect? Well, in order to try to solve the validation problem, a range of techniques have attempted to solve it in kind of solve different sub-problems pertaining to validation. One key method, which is still being used as late as last year, is to simply replicate about half a dozen experiments that were published in the late 90s. One of those includes the fish oil Raynaud syndrome connection I talked about before. Well, clearly this doesn't scale. Some methods will try to perform a more cohesive analytical approach on a subdomain of medicine. For instance, if you're just concerned with genes and diseases, you can create a hand-tuned statistical model that helps you understand that. But Moliere is a very broad system that's trying to use all of medical information, so we can't take advantage of these fine-grained statistics. You can always have an expert sit over your shoulder and watch. This is what we did to begin with Moliere, but of course that uses the expert's time and increases bias. And the gold standard, of course, is to have your system produce something that you can ultimately publish. And showing that your system truly accelerates research is the best you can do, but clearly that's expensive and comes with its own set of biases. In order to try to solve this problem, we're going to turn to a large-scale solution, wherein we can create a bunch of potential positive and negative results and use the fact that we're going to be performing thousands of queries to kind of smooth over some of the concerns about true and false positives on the margin. And additionally, once we have some ranking criteria that allows us to evaluate large-scale positive and negative samples, we can evaluate that ranking using some existing machine learning metrics, which will give us a numeric score to the overall aggregate performance of the system. So we just need to solve those three problems. The first two are pretty straightforward. We need to collect positive samples, and to that we can turn to our data set of predicates. Those are those subject-verb-object statements defined on some coded terms. And it turns out, looking at the Medline data set, that there are more new predicates added every year than all prior years. This means not only do we have a large wealth of training data to look into, but we can expect that there will always be more interesting research to help validate our system going forward. It solves some scalability problems I talked about. So what we're going to do is we're going to pick some cut date. In these experiments, we picked 2010. We're going to train the system on data prior to 2010 and try to predict the new research that's been published after 2010. We're going to compare that new research to negative samples. These negative samples are just randomly selected terms such that there is no known connection between those terms. Now, surely we might randomly sample some good ideas, but we're going to do so at scale, so that should happen at a very low rate. And surely the negative samples we choose to select are not going to look exactly like ideas that a human being could have come up with. We're going to address that problem later in the dissertation, but for now, this actually does give us a simple and scalable approach to begin solving the validation problem. So now all we need to do is come up with a measure that will rank those positive predicates above those randomly sampled predicates. We select a couple of different metrics that are based on some heuristic understanding of what the data set should look like if a predicate were publishable. For that, we first turn to embeddings, and we come up with a couple of measures, such as if the two query terms are close together in our word embedding, then they ought to be talking about the same thing, and therefore the predicate is more likely. Also, if the topics that we uncover correlate with both keywords, or if they bridge the gap semantically, meaning they spread throughout the embedding space between the two terms, then we again can expect a lot of conversation about both terms, and therefore the predicate is more plausible. There's a number of ways we quantify this, but we extend this analysis by looking just at the network of topic models. So here, two topics are connected if they share relevant keywords, and they're also connected to the elements of interest, A and C. And we observe that if there's a high connectivity between our two elements of interest, then the predicate is more plausible. And if there is a low connectivity, then there might not be enough information, again, bridging the gap between our two keywords. Now, there's about 12 different ways we've quantified both the topic network and the embedding-based measures, but we don't know which of our heuristic understandings are the best. For that, we train a polynomial combination that learns to combine signals from each of our proposed heuristics. And we use that polynomial to rank about 8,500 queries. Half are positive and half are negative. And here we can finally start to see overall system performance for Moliere. We see the polynomial method gives us a 0.83, which is not a magic number, but it does begin to give us a criteria upon which we can iterate Moliere in order to get better overall performance. looking at some of our other heuristics, particularly this L2 that scores a 0.78, this represents the Euclidean distance in the embedding space between our two terms. It has no relation to the rest of the topic model process. So this tells us the information conveyed just by the text and the text embedding, and the delta between L2 and the polynomial method shows us the added benefit of the whole topic modeling approach. This was a very important realization for us, and this is going to help us both understand Moliere performance and propose a new method going forward. But you should have a problem with what we just described, because we proposed some positive and negative samples, we proposed the Moliere method, and we proposed the ranking criteria upon which we're going to evaluate our samples. Because we had control of all the pieces, you don't know whether or not the Moliere system will actually function in the real world. In order to evaluate that, we turned to the gold standard in validation. We worked with our medical collaborator, Michael Stutman, and we performed 40,000 queries wherein we compared HIV-associated dementia to every gene in the human body that we could identify with Moliere. We ranked those different connections based on the measures that I just described, and we identified the gene DDX3, which was highly ranked, and we didn't expect to see it in this list. We performed some laboratory experiments and found that on mice brain cells that had the HIV TAT mutation, which is consistent with human HIV-associated dementia, that if you turn off the DDX3 gene, this brain cell has a better chance of surviving the aging process than a brain cell where this gene is left on, in which case the brain cell develops dementia-related symptoms. So this demonstrates that the measure we came up with in our own sandbox experiment actually does apply to the real world and gives us some confidence that we can trust our validation approach. So now that we've proposed this method of evaluating system performance, and we believe we can trust it, we can now answer some questions about Moliere. The main question we'd like to understand is, are abstracts good enough for hypothesis generation, or should we take the time to invest in full text versions of these papers? We answer this question in another paper we published in Big Data. Full text papers are great because obviously they contain all the detail you should need to understand a new connection in medicine. They contain tons of auxiliary information, which can be really fruitful for finding those unintuitive connections within our networks. But full text papers are logistically challenging. Oftentimes they only come as PDFs and they can be hard to parse. If you've been submitting your resume to any of those PDF parsing websites, you know that oftentimes these make mistakes. Full text papers are also noisy from the perspective of our analysis. They contain a lot of information in images and tables, which we don't really have access to. And ultimately, publishing companies would like you to pay for full text papers, rightfully so, but it's hard to do big data analysis when you're spending $30 per data point. So in order to address some of these challenges, we turn to a data set called PubMed Central. It gives us 1.5 million full text papers that have already been parsed so we can get a plain text release. This is not close to the wealth of biomedical information, but it gives us some points of comparison. We create different versions of Moliere trained on some underlying data sources. We first take the set of abstracts corresponding to PubMed Central articles. That way we can compare the model trained on those abstracts to the model trained on the full text versions of those same papers. We can compare that to different versions of the Medline dataset, which is the dataset we've already been talking about. And we take iterative halves of Medline to understand the increase in performance provided by more papers that might not be as related and don't contain as much information as their full text counterparts. And we run a bunch of analyses. We're going to focus on one particular analysis in this presentation, that is the comparison of our method given the polynomial combination ranking and the Euclidean distance ranking. So in blue, we see total system performance for the benchmark. This experiment set corresponds to training Moliere on data up to 2015 and predicting recent published predicates using the methods we already talked about. Well, the blue bars indicate the polynomial method is the best possible performance, and we see full text papers clearly do the best with a score of 0.79. However, when we look at the Euclidean distance measure, that's the green bar, and it indicates the amount of performance gained just by the embedding space, we actually see, well, again, that the full text papers perform best, but the difference between the bars, the added bonus of using the full embedding or the full topic modeling based approach, is actually the smallest for full text. This can be seen qualitatively when you look at the topic models, as full text papers can be noisier and produce less interpretable topic model results. Interestingly, the abstract versions of these data sets provide better topic models, but you oftentimes just care about your global ranking criteria. However, in order to rank predicates using the full text data set, it takes 45 times longer to perform a single query, primarily due to some limitations of the LDA topic modeling algorithm on longer documents. Therefore, while full text papers can be really good for understanding some fine-tuned information or some hand-selected information, it would be kind of infeasible to run this type of experiment on our big 40,000 gene query. This is now one query per hour rather than a query per couple of minutes. So we've just looked at different ways that we can evaluate the Moliere system. We can rank Moliere results, and we can evaluate the quality of Moliere input. We're going to use the intuitions we learned in Moliere to take a whole new approach to hypothesis generation. This is the system Agatha, and it's the method we just wrote and currently have in submission to KDD. The Agatha system is going to really challenge some assumptions we had with Moliere and give us superior performance as a result. So Agatha replaces a lot of our assumptions. Instead of doing slow graph and topic model based analysis, we're going to replace that with very fast deep learning inference. Instead of using the ranking heuristics that we came up with ourselves, we're going to let the model learn from the data its own ranking criteria. And rather than focusing on abstracts, which are relatively focused but can contain a lot of extraneous information, we're going to look at just sentences within our node, where each sentence is its own considered element, which we view as the smallest, most atomic statement of information within our biomedical text. The Agatha pipeline is pretty sophisticated, and I'm going to leave details for the dissertation, but it's important to note that we're using the same data set that we used for Moliere. We start with Medline, and we parse out each of the abstracts, and we continue to parse down to each of the sentences. These sentences can be split into each of their terms, called lemmas, and combined, the terms can be combined to form entities and phrases, which we're calling n-grams. All of this information can be combined with our set of predicates, those subject, verb, object statements, as well as our coded terms provided by the Unified Medical Language System to form a semantic graph that is similar to the Moliere graph. A key difference is that we are not going to perform any shortest path queries. Instead, we're going to perform a graph embedding that allows us to train a ranking criteria directly from this biomedical information. Let's dive into some pieces of that. The semantic graph is pretty simple. We have sentences, and two sentences are given an edge if they are containing similar information based on a more recent word embedding technique. Each of these sentences contain terms and phrases. We can make new nodes for each term and phrase and combine or make edges from those phrases to the sentences they occur in. We can additionally combine all of the predicate statements as new nodes and connect to any sentence that uses the predicate or any term used by the predicate. In 2015, in the data up to 2015, we have a network of 188 million nodes, and this is the network we're going to perform our analysis on. This is a very big network and contains a lot of information, so we're going to need some sophisticated modeling techniques. It's important to note that in the 2020 release that we just created, that gains even more nodes, going to 270, really, I think, selling the big data aspect of this problem. So we have a big network and we want to understand a lot about it, so we need to turn to some sophisticated modeling techniques. We use the transformer encoder model to ultimately learn our ranking criteria. And I'm going to break apart the components of this model. We're going to start at the objective we choose to optimize and walk our way backwards through how we model predicate ranking and how we ultimately get our graph embeddings. I find this is the most intuitive way to understand why we made some decisions that we made. So let's start at the end with the function we're optimizing. Alpha and beta in this function are some known connection in our network. So we would like the model to prioritize the alpha-beta connection. We choose to optimize margin ranking loss. So we have to perform some ranking against some negative samples. We're going to compare each positive sample between a particular alpha and beta to about 50 negative samples. They're going to come of two different types, negative scrambles and negative swaps. We'll talk about that in a second, But ultimately, the positive samples represent good information we'd like to predict, and the negative examples represent types of incorrect information we'd like the model to learn to downplay. And we optimize margin ranking loss. This means that the ranking criteria output by our model, called script H, needs to be at least some margin larger for the positive example than each of the negative examples. So let's dive into this a little bit more. A positive sample, which is given to the model, contains some components. We have alpha and beta, which are going to be the embeddings of the two terms we care about, but we need to give it a little bit more information about the underlying predetermined knowledge that we already have about alpha and beta. So for that, we sample these gammas. These are known predicates associated with alpha and beta, and we're going to sample from the disjoint set of both nodes' neighborhoods. This means that the model will never see a direct alpha-beta connection. Therefore, it will never learn the trivial relationship of, oh, there already exists a shared neighbor, so let's predict 1, and if there's not a shared neighbor, let's predict 0. This is really important for extending the model into the future. So that's a positive sample. How do we get negative samples? We would like to prioritize that above something. Well, we have two types of negative samples, as I mentioned, the scramble and the swap. The scramble is easy for the model to determine because it's just malformed input. And this is a very important negative sample to have because it really helps the model in the early steps of convergence to gain some basic understanding of the graph embeddings. Well, we sample X and Y, which have no known relationship, and we sample a bunch of gammas that have no relationship to X or Y, which is why this is a malformed input. The swap, on the other hand, is a harder example for the model to distinguish. We again sample X and Y where there's no known relationship, but now the gammas, which are prior knowledge related to X and Y, are sampled appropriately. To determine the difference between a positive sample and a negative swap, the model actually needs to pick up on some biomedical domain knowledge. So that's the function we're choosing to optimize. Now we just need to form some model that will output our ranking criteria. For that, we use the transformer encoder. At a very high level, the transformer encoder is a model that's going to take a set of embeddings as input and perform all pairs comparisons to form a new set of equal size of output embeddings, where each output embedding is determined by all input embeddings. This means that we can take the average output embedding to represent the accumulated knowledge of our predicate. That average output embedding is here represented by script M. We can project that to the number line using a transformation matrix W and chunk that to the domain 0, 1 to get our ranking criteria, script H. So now we just need to understand the encoder block, which is that building block that takes n inputs and produces n outputs through a mechanism called multi-head self-attention. This is the main component of the transformer model, so we're going to talk about it in a little bit more detail. Attention is conceptually a set of learned weighted averages over your input. Here, Q, K, and V are stacked matrices where each column corresponds to one of your input embeddings. And we're going to learn K, Q, and V such that the Ks and Qs act as a key value matching. So if the K and the Q have a high dot product, that's going to correspond to an increase in the weight of an associated value from the V matrix. This is self-attention because K, Q, and V are all going to be derived from the same input X using different transformation matrices that we learned during training. And it's multi-head self-attention because we're going to perform the attention mechanism multiple times and join them together with yet another transformation. Okay, so this is the main mechanism to which we take n input embeddings and produce n output embeddings, in addition to some normalization and residual connections. So now we just need to understand the graph embedding that gives us our initial set of input embeddings. And then we can fully understand the Agatha model. Well, we're going to use a method called the PyTorch Big Graph Distributed Graph Embedding. This is a tool set that allows us to perform an efficient graph embedding on our whole nearly 200 million node graph. It is going to perform a same pattern that we've seen before in graph embedding. We're going to start with observations. Here the observation is two nodes are similar if they share an edge. And we're going to fit the observations to a set of embeddings. Here it's the E function, except we're going to use a kind of funky similarity measure. We're going to be using a biased transformed dot product. So the transformation corresponds to the types of nodes in our semantic graph. Each edge type is going to have a unique transformation, for instance, between sentences and n-grams. The transformation is going to modify one of the two embeddings, in this case, the embedding corresponding to node J. And we're going to use the first dimension of both embeddings to bias the relationships in our results. This is because some nodes, by quality of their behavior in the network, are simply just going to have more connections than others, kind of irrelevant without respect to the rest of the features. For instance, we can always expect to see new connections to the cancer node. Now, the rest of the information helps fine-tune what we've learned from the bias, and that comes from the transform dot product of the rest of the embeddings. This method, while it looks kind of strange, is actually fairly standard for heterogeneous graphs of the size we're dealing with. The method that we use to learn graph embeddings is to minimize softmax loss of each edge against 100 negative samples. This should seem familiar to the Agatha objective because we do have a large negative sample component, but it's important to note that we're going to learn our graph embeddings as a pre-processing step to learning the Agatha model. So this is all done before learning the particular ranking criteria. What I'm showing you here is the loss associated with a particular IJ pair, and we want the similarity associated with I and J to be much greater than the similarity associated with 100 randomly sampled XY connections. More details, of course, in the dissertation. So now I've gone through the whole Agatha deep learning model, going from the graph embeddings through the ranking criteria. We've done a lot of work, so let's talk about what we get for all that work. Well, this is the same comparison we looked at a couple slides ago, where we looked at different versions of Moliere given the same baseline, or given the same baseline predicate set. Well, we trained Agatha using the exact same training data as the 100% Medline example. And we ran the new ranking criteria to prioritize the same set of predicates. We see here an increase of performance from 0.71 in the 100% Medline case to 0.9, which is substantial. We also see an improvement when comparing the full text versions of these papers to the Agatha version. This shows us that we can gain even more information from the set of abstracts than the Moliere system could gain from full text versions of these papers. And a big result that doesn't totally show up on this graph is that of the runtime. So I mentioned before that the PubMed Central full text version could take up most of an hour for particular queries. Well, the Agatha system can now perform hundreds of queries a minute because we've replaced our graph analytic and topic modeling based approach with a stricter deep learning based approach that is more parallelizable. In addition to this increased speed, we've also gained access to a new type of query that would have been infeasible for Moliere. This is going to address the challenges we faced with the negative sampling based approach. Now, rather than taking random negative samples, we can look at all pairs of connections within interesting medical subdomains. This way, we might only have 100 good connections within a particular type, for instance, 100 known connections between genes and diseases. But we can try all 10,000 pairs of gene and disease and see if the Agatha model can rank those 100 known good pairs higher than our 10,000 bad pairs. In this way, the positive and negative samples will look the same. They're both relationships between genes and diseases for that example. Also, the ratio of good example to bad example is going to fit the real world a little better. There's certainly more bad ideas than good ideas. We ran this type of analysis on 20 popular biomedical subdomains. I'm going to mention a couple. We looked at gene to cell function. This was the most popular, or the highest performing of our 20 considered. We see an area under the precision recurve curve of 0.44, which is actually very high for such an imbalanced problem. But more tangibly, we see that if you rank your 10,000 potential predicates, half of your top 10 are going to be good ideas, and the top ranked predicate is a good idea. Additionally, if you decompose the gene to cell function all pairs relationship to a set of one-to-many queries, you can now expect to see your good cell function to be ranked within the first two results corresponding to each particular gene. Now we see high performance for gene to cell function, we see similar performance for gene to neoplastic process, and we see similar interesting subdomain results for a whole range of 20 popular biomedical subdomains. The results of that are going to stay in the dissertation. So we have now explored a whole new way to use deep learning-based approaches to accelerate research in a way that extends what Moliere was capable of doing and challenges a lot of the assumptions we held for Moliere. So now that we've got a very robust ranking measure, we're going to use similar deep learning techniques to try to get more information for a smaller set of queries to a biomedical researcher. For that, we proposed this paper for conditional biomedical abstract generation. This is actually also in submission to KDD. I wrote this paper at the same time as the Agatha paper. It was a lot of work. The end goal would be for the user to supply 2 keywords and allow Agatha to output some ranking criteria that can tell you which of your keywords you ought to prioritize. And ultimately, information learned by Agatha should be able to be used by some extra model to help produce a textual description. In order to do this, we're going to be talking about conditional language generation. But because the Agatha system was being developed in concert with the CBAG model, we're not going to yet be able to output Agatha directly into this model. Instead, we're going to look at a range of ways you could condition text in order to generate useful biomedical abstracts. But first, let's give you a little bit of background on the conditional language model. A language model from the perspective of natural language processing is just a probability distribution wherein each element of a sequence is estimated given all prior elements of that sequence. This becomes conditional when you add in an extra a priori term, wherein we can determine the types of keywords we choose to predict based not only on the sequence, but also on this known condition. We can generate new text by iteratively sampling this distribution and feeding subsequent tokens in to input in order to ultimately gain new understanding of our text. So at a very high level, the CBAG model, as we've trained it for this paper, is going to take metadata associated with each abstract, including the year the paper was published and any keywords the author has chosen to associate with this paper, as well as the text that the model has been generating in order to output the next token. In more detail, the CBAG model is a full transformer. So the Agatha model was only a transformer encoder, and it should look similar to the left-hand side of this diagram. The right-hand side of this diagram is the transformer decoder, which is going to use signals we've learned about our condition to help us predict new text. And just like the Agatha model, where we started at the objective and worked our way backward to input, we're going to do the same in this example, starting with our multitask objective. See, it turns out that just predicting biomedical text tends not to be enough to really enforce domain-important keywords and understanding for the model. So instead, we augment our text with parts of speech, dependencies, and entity types, so that our text prediction model needs to also understand common phrases and keywords used in medicine. We optimize the following objective. Each task within our multitask objective is given a different term, but each term ultimately is the same formulation. We are minimizing negative log likelihood, where the output of our model, again script H, but now referring to the CBAG model, is going to be projected using a different transformation per task to the prediction space associated with each task in a multitask objective. And we're going to minimize negative log likelihood between the set of text and annotations we have access to versus what the model believes to be likely. I mentioned annotations. We need to know the parts of speech dependencies and entities for all 30 million papers found in Medline. But of course, that data set doesn't exist. What does exist are very small scale, human-explored, biomedically relevant data sets. And there's a number of pre-trained models that have demonstrated very strong performance on both these small-scale data sets and applying to new test sets. Well, we turn to a package called SciSpaCy, provided by the Allen NLP group, which has been trained on a biomedical model that can classify entities, predict dependencies, and determine parts of speech. And we apply that to all of Medline. Because we're taking a small-scale training set and applying it to our overall unstructured training set, we're calling this overall method semi-supervised. So now that we understand our objective, we just need to understand how we get there. And this is a full transformer model which uses different versions of multi-headed attention. Before, we just focused on multi-headed self-attention. Well, attention, again, is just a learned weighted average over your input, where we learn key value relationships that can help us prioritize different input signals. It becomes different versions, not just self-attention, when we add in this extra term. So now the query set can be determined by one set of inputs, and the keys and values can be determined by another set of inputs. This is what allows us to build some different behaviors into multi-headed attention. Here's the full model. The math is there for reference, but I think it's easier to look into our diagram. We see in yellow the condition, which is our encoder, and it corresponds to the script E on the left-hand side. The keyword and the year and the keywords associated with this abstract are each looked up and given a unique embedding. And these embeddings are compared using the self-attention mechanism we've already talked about. Now that is output to the decoder. The decoder, which is script D on the left-hand side, begins by taking our input text, adding to each embedding a positional encoding, and then performing masked self-attention in order to give us that behavior where subsequent tokens are predicted using prior tokens. Then the encoder and decoder stacks can be combined together using encoder-decoder attention. This takes queries from the decoder stack and keys and values from the encoder stack. That can all be combined to give us one embedding per token that can be used to predict each task in our multitask objective. And so that, from text onward, is how we get our abstract generation. All we need to do is clarify the ways in which we formulate our input text. The year and mesh terms can all be given unique embeddings, but biomedical text contains millions of different keywords, and it becomes infeasible to model each one uniquely. In order to get over some of the limits of the text embedding models of the past, transformer-based text models all use different iterations on ultimately this word piece algorithm. We're using a method called unigram subword regularization, which I believe was published in 2018 or 19. Each word, rather than being given a unique embedding, is going to be split into chunks of characters. Now, the simplest chunking could be to chunk each character individually, but this can lead to very, very large inputs. What we'd rather do is learn relevant chunks that are used often in medicine. For instance, we can identify that the word immunosuppressive contains the letters suppress, which we expect to see in other contexts. This way, we can learn that the component suppress means to downplay something, and we'll give that understanding to the overall term immunosuppressive. This method is different than other subword tokenization techniques because it performs subword regularization. This means that rather than being dependent on any particular tokenization, we're going to choose one of these tokenizations each time we encounter the word immunosuppressive at runtime. So the model will see multiple different ways to look at the same word, which ultimately increases performance. So why does that work? Well, it works computationally because we can fix the number of subword units. We choose 16,000, which is a typical selection for a problem of our size. These each start as different random embeddings, and we can learn them while predicting our abstracts. And we can gain an understanding for the full word because we're applying this masked self-attention mechanism, wherein each subword unit will first be given a positional encoding or be augmented by a positional encoding, which tells us where that word occurred in the sentence. And then when these embeddings are joined together with attention, we eventually get an embedding for the whole word that is context sensitive. And this is the mechanism to which we can use a small number of subword units to construct all of the words in medical text. Okay, I've now explained the way we get our text, how we put it through the transformer model, and the multitask objective we use to understand medical text at training time. So now let's talk about some of the results we can get from this model. We perform our tests by taking 30% of Medline and holding it out during training. Then we're going to try to generate text related to each of these test set abstracts. For each of them, we're going to take the year the paper was published and any keywords the author chose to associate and feed them as input to the model, as well as the human written title that corresponds to this particular abstract. Now we're going to let the model generate a whole new paragraph of text until it decides to use the end of abstract token, meaning the abstract can be of whatever length the model decides. And then we can compare the text output from the model to the text output by the human corresponding to the same title using a couple of different metrics. Now, there isn't a great point of comparison, but the GPT-2 model provided by OpenAI has 1.5 billion parameters and has demonstrated some really interesting performance on a range of domain-specific tasks. So with lack of a specific baseline to compare against, we're going to compare our generated text versus text generated by the GPT-2 model given similar input. The GPT-2 model is not conditioned, so it lacks some of the information we have access to. And it was trained on a large set of internet data sources, such as Wikipedia and English literature. Now, again, it's been shown to provide interesting results as a knowledge base to many different applications. And we're going to see it perform remarkably given the fact that it was trained on out-of-domain data. So without further ado, let's take a look at an abstract. So in bold, we see the title the human wrote, and we see the text output by our model. Note that the text is all set to lowercase simply to make comparison and evaluation a bit easier. And the bolding I added as a way to demonstrate in this slide some different phrases that the computer comes up with that are non-trivially related to the title, but do correspond to information relevant to the topic we're discussing. This corresponds, such as a cross-correlation function or the high-throughput imaging of biomolecules. Additionally, note that the length of this document is about the length of a typical abstract, and we see that to be consistent across the full training set. What's not described here, but what I think is a fun side effect of this model, is the model often tends to predict things like p-values, and the distribution of fictional p-values that the Sybrandt model outputs is actually identical to the set of p-values reported in medical literature. So it's also picked up on some interesting biomedical cliches, if you will. Now, the GPT-2 model outputs a different look of document. It produces some new line characters, which I represent here with our bracket/n. And we see that it is, because it was trained on internet resources, it is discussing things like artificial neural networks and someone's blog. In this example and across other examples, we see that the model is outputting what to me looks like a blog post discussing a scientific result rather than the scientific result itself. Now, clearly, it can still uncover some interesting engrams, like this vision, impaired vision with retinal implants phrase, which I think is interesting. But we're going to see across a number of quantitative measures that the Sybrandt model is able to better predict non-trivial engrams when compared to this GPT-2 model. Now, caveats aside, because of course the GPT-2 model has been trained on different types of data, we do see that a focused approach for the problem of biomedical literature is very valuable. And we're going to see in a second that the condition is also really important, which is going to be useful whenever we want to extend this approach for hypothesis generation. Looking at the condition, we begin our generation with the phrase, "in this study we found." And we ran a number of experiments where the only thing we changed were the condition phrases associated with this generation. And we see that if we supply the condition term DDT, that all of a sudden the model starts talking about things like algae and pesticides. If we instead talk about gold, the model will now talk about nanoparticles and ion interactions. If we give it fish oil, we start talking about diets. Here we see that the condition component of the model is actually very relevant to the overall generated text and gives us more intuitions that we could apply a method like this to generate text descriptions to associate with Agatha outputs. And so thank you for sitting with me for about this last hour. We've gone over 7 first author publications and a wealth of work that's happened over the last 4 years. I'd like to take a second to thank my committee, who have been very flexible with all the technical glitches that have kind of come up through this uncertain time we're in. And I'd very much like to thank my co-authors, Michael Stutman, Ruslan, and Ilya, who have worked on a bunch of different subcomponents of the chapters we've talked about. Furthermore, I'd like to talk and give a thank you to the different funding agencies that have provided me some fellowship opportunities over the course of my PhD here at Clemson. And so without further ado, I'd be very happy to hear questions.
All right. Virtual applause.
Yeah.
Okay. Do you have any questions? Open questions before we disconnect the YouTube streaming?
Yeah. Yeah.
Questions? Most of microphones are muted.
Yeah.
Alex, Brian, Amy?
I'm actually good myself.
Great.
Okay.
I'm very impressed.
Well, thank you. We can leave all the baseball bats for the closed door session.
Okay, so let me ask a question and let's discuss something. Well, we have an excellent quality of Agatha, right? And we have an interpretability of Moliere. So clearly Agatha is less interpretable. So what do you think? It's more a future work question, how to combine the quality of Agatha and interpretability of Moliere?
Well, there's always the potential to run parallel queries, which we've actually already implemented, where you might run Agatha to quantify maybe your couple thousand different elements of interest. And then for a subset that you believe to be of, some interesting priority score, you can switch over to a more interpretable method. I think another thing that we could continue to explore would be some non-textual, potentially like visualization-based approaches where we could look at correlations within the network structure as well as correlations within text. So I very much view the interpretability as kind of an add-on component.
Certainly, yes.
Yeah. Although it's worth noting that the transformer model in some specific cases can be interpreted. So for instance, you can look at the weights that you learn through your key value queries in order to understand which input embeddings were most highly prioritized. This could tell us, for instance, the set of predicates that the Agatha model believes to be the most relevant into making its ranking, which could influence our analysis. But I think that that's a little bit more, that is definitely a tangential approach to what we've talked about.
Yeah, right.
Justin, this is way off the beaten path from what you've been doing, but at one point you mentioned that full text is noisy. It has all these images and things, and you focused on text. Do you think there's any way that you could analyze images or some kinds of images with these techniques? Maybe charts might be special, or not random images.
So clearly any special image case could be like fine-tuned. I think charts would actually be a really interesting thing to look at. For instance, try to read the horizontal and vertical axis and then pick out your data points and then just convert that to a matrix and see if you can use it. It could be interesting. And there's also so much work being done in image captioning that my gut response is to learn a model that predicts captions given figures, because of course authors do include captions to their figures. Whether or not they're very valuable is another question. And convert it into a textual source that then we can take advantage of using existing methods. Did I answer your question?
Oh yeah.
Right. All right, great. Is there anything else before?
Any other questions?
Yeah.
Before we disconnect the stream? Okay, so here's the protocol. We're going to talk to you without the stream, without the YouTube stream, right? And then you'll need to disconnect, and then I will Slack you,
Okay,
and then you'll come back, and then you'll come back.
Great. I'm going to disconnect the YouTube stream. I have to do it from the other room for 1 second.
Okay.